Let's try to understand how we define a semiconductor with the help of energy level diagram or energy band diagram. Now, first thing is, you guys have to understand what is an energy level diagram, correct? Or what is an energy band diagram. See, when it comes to energy level or energy band diagram, or energy band, for example. Now, every material has a particular structure, first thing, correct? Like either it is face centered or it is body centered. Depending on the structure of that particular material, there is an energy associated with it. Okay? And let's come down to atomic level. See, every atom has valence shell in it, correct? Now, since we are talking about semiconductors, conductors and insulators, these three materials, they have valence shell. Now, what happens in most of the times? You have electrons in the valence shell. If all the electrons are paired up, or if all the electrons are bound to the atom, we say that the valence shell is empty. Correct? Empty in the sense, it is either completely full or it is empty. Correct? Now, if there are free electrons, like what happens in conductors, metals, here what we have, you have electrons in that and electrons will start to move. This is when we say that we have electrons in the valence shell. Correct? Now, what happens in a conductor? There are valence electrons. In the sense, those valence electrons can easily move in that particular crystal or structure or whatever you can call it. In insulators, the energy between the atom, the nucleus and the electron is a lot compared to that of conductors. So, in insulators, the electrons are bound to the atom. That means there is no movement. That's why they are called as insulators. Okay. Now that you have understood that there has to be some sort of an energy here. So for a semiconductor, this is in between. That means it cannot freely flow also, like what happens in conductors. Or it cannot even, it's not completely bound to the atom also. It's somewhere in between. That's how we define a semiconductor with the help of energy level diagram. Okay. Now, when we talk about energy bands in the sense, so there are energy levels, correct? Now, there are two important parts here. One is called as valence band. Second one is called as conduction band. Alright. Now, valence band and conduction band, these two are extremely important for any conductivity. Okay. Now, what happens is, you have valence band and conduction band. The material starts to conduct electricity or current only if the electrons will jump or electrons are in the conduction band. See, when I'm talking about bands, valence band has one energy level, conduction band has another energy level. They are in a different energy levels altogether. Okay. So, this energy level is a very, very important part. Like what level is the valence band? What energy level is the conduction band? Depending on this, we define three things. Again, conductors, insulators and semiconductors. Okay. Now, see, when you have this energy level, collection of these energy levels, we call that as energy band. For example, look at this picture. Okay. So, in this particular figure, what you have energy band. You have different levels of energy level. Now, what you're seeing, see, you guys saw that there are two levels, correct? Now, one is the valence band, one is the conduction band in these two levels. Do you see that there is a gap between these two? That is called as the energy gap in the material, okay? Or energy gap between the valence band and the conduction band. Now, depending on this, we have different types of material. Okay, depending on this only, we talk about conductors, insulators, semiconductors. For conductors, what's going to happen? So, look at this one. This is for a conductor, the figure what you're seeing. Now, see, you have conduction band, valence band. They are overlapping each other, correct? Overlap in the sense, when you have an electron in the valence band, it will directly go to conduction band. Because both of them are overlapping each other. I don't have to provide any energy to it. Electron will, as it is, it will go. This is what happens in a conductor. That's why even if you give like a small voltage, that's good enough for a conductor to conduct the current. Because the valence band, conduction band, they overlap each other. This is what happens in a conductor. For an insulator, see, this is the image. What happens in an insulator? You have valence band, conduction band. The energy gap is more than 3 electron volt. That's a lot of energy. Okay, it's a lot of energy. Let's think about it. One electron, that needs more than 3 electron volt of energy, correct? And there are like, billion is a small number. You have 10 power 19, 10 power 20 electrons. Where will you give supply so much of energy? That's why the materials behave like an insulator. There is a huge gap between valence band and conduction band. In valence band, you have the electrons. But in conduction band, there is nothing at all. Correct? There is literally nothing. That's why this energy gap causes the material to become an insulator. Alright? Or the other way around is actually correct. That means the material has so much of energy level. That's why it is an insulator. Now, semiconductors, it falls in between these two. That means in semiconductors, they don't overlap. Okay? Or they're not very far apart also. So, for a semiconductor, this is what you have. It is less than 3 electron volt. In the sense, if I give enough energy to it, it will become a conductor. If I remove that energy, it's an insulator. So, something like this. Okay? This is how we define a semiconductor with the help of energy level diagram. Okay, based on the conduction valence band, conduction band and the energy gap, how far or how close it is. Based on that, we define a semiconductor. So, two ways of defining a semiconductor is done. One is with respect to resistivity and the second one is with respect to the energy band diagram. Now that you know that we can define a semiconductor using two ways, in the next one we'll see types of semiconductors.